Okay, so here we are back on the Heresy Radical synthesizer, and last time we got to the point where we hopefully have a means of reading our string reliably without too many dropouts caused by poor contact between the string and the I don't know what to call this, wiper I suppose. I have to think of a consistent name for it. And hopefully got that smoothed out so no zipper or any other sort of noise is going to get through from that into our audio. So I have written the code to do this, so let's evaluate what I've got and see if it's going to do what we want it to do. Okay, so let's see how this performs. So let's first do a slow. Run up and down, and then we'll do a fast run up and down. And we will do one of those, and we will now, I will now press very gently, so we're going to hopefully get some bad contacts to see how it behaves with that. Okay, so let's get our results up on the screen and see how we've done. Okay, so here are our results. Now here on the top trace we have the raw data coming in from the string as read by the STM32, and on the bottom we have the conditioned to try and stop dropouts. So you see it seems to be working pretty well on our slow up and down, and on our fast up and down, we'll have a look at this. The problem we would be looking for here is whether we're slowing it down with limiting the slew rate, and it doesn't seem so, and why this value here is not going to 0 when this value, when it should be, I do not know. That's something to look at. And if we look here where we've changed the values suddenly, you can see here it goes down there suddenly, and here it takes me, what's that, 150 milliseconds to drop down. Is that too slow? Maybe it is. We shall have to see. And here this is where it was going slowly, but with me just resting my finger lightly, trying to deliberately try and get bad contacts. And if we look at this section, we can see at the top, yes, there are some dropouts there, and we've done our best to get rid of them. I think that's the best we can do. We're just going to have to press hard and make sure the contacts are clean. However, we do here have something worrying. The conditioned input has dropped out and gone to 0 when the actual input is perfectly fine, so that's a little bug. Don't know what's happening there. That's one to flag up. So now if we go to the this is the smooth value, which we're actually using to control the pitch of the audio, and this at the top is the audio, which we'll listen to in a minute. So let's just have a look at the spectral view of that. And yes, there are some digital noise elements appearing here. It's hard to say with the fact that it's a sine wave which just overloads the FFT. And here we have, well, some. There is some here, so maybe our filter isn't quite good enough, but we are going to go with it for now. Something else to flag up, and let's have a listen to it. Now we want to listen to this side only, because that side will click. Yeah, you can see it just dips in pitch there. And what that is, I don't know. No, it doesn't sound too bad for its maximum slew rate. And what's going on here? It's not bad up to there until we get to there, which was the one which was that bug for somehow where it dropped out, the condition signal dropped out where it shouldn't. And these, it's dropping out there as well. On both channels. Yeah. Okay, we will look into that. I might spend a bit of time on my own looking into that, but I think we together are going to move on and look at the turntable, the rotation sensor. Okay, so the turntable, every 3 milliseconds we get a position, an absolute position in degrees. Well, 4096 is one rotation, so it's in 4096th of a circle. And what I'm doing to calculate speed is simply subtracting the last reading from the current reading and calling that the speed, and then smoothing that with a simple running average type smoother to form a speed value, and that speed value is controlling linearly the level of the sound, and it's just one tone, as you'll hear. So if I turn this, so it's working, but especially if I turn it slowly, yeah, we can hear some nasties going on in there. So let's actually look at the results and see if we can do something about those nasties. Okay, so this is the audio we've recorded, and we'll play this through with the file. Okay, and you can hear it warbly and rumbly, and here I wasn't actually moving the turntable. This is where the turntable has stopped between two values, because it's digital, one
there's only 496 values per rotation, and it's bouncing between two, and even with smoothing that we get an output. So that's not acceptable. Possibly I can put some hysteresis on it to stop that happening, but anyway, we also get this sort of warbling, rumbling sound in the main section where I was moving the turntable. So let's now have a look at the signals coming from the turntable, the speed signals. If we look at that, okay, top trace is the raw speed calculated by subtracting the last value we received from the current value, and the bottom trace is that smoothed by, again, our running average, the same we're using on the string. And if we listen only to the bottom value, the bottom trace, so this is the one we're actually using to drive the level of our sound, you can hear all that rumbling and grumbling. So the problem is actually low frequency, and again here we get that rumbling. Should we stop this? Yeah. So that is simply not good enough. We can't do with that nasty digital noise getting into the audio from the turntable, so we're going to have to think of something better by way of conditioning the turntable signal. Okay, so here is what we are doing. Now we get an update on the position of the turntable every 3 milliseconds. So if we look at position, we'll get something like that, where that is 3 milliseconds. And what we're doing to find our speed is basically taking that value and this value minus this value, giving us, so that's 0, something like that. So that's somewhat exaggerated, and then trying to filter that to that. I haven't drawn that very well, but you get the idea, and that is rubbish. That is not doing us any favours at all. We found it makes a nasty rumbling noise. So what I am actually proposing to do is this. So position, we've got, drawing this a much different scale. Now instead of trying to crudely measure position, so that's speed and filtered speed. So instead of trying to measure speed and then filter it, we're going to filter the position and then measure the speed of that filtered. And what we are going to do, so this is time going on, we are going to use an FIR filter, which takes basically an average of a number of samples, and I did a tutorial on FIR filters, and at the end I went into this one big special case one because it's very easy to implement. So we've got an average of these samples, and we're going to take another FIR filter and take an average of these samples. So if this is going up roughly in a straight line, this will be this value and this value. So we are then going to subtract, I call that in the code pos and neg, neg. So speed equals simply pos minus neg, and that gives the speed, average speed over this period. Now as long as these aren't too long and cause a delay between the current position and the actual speed value, which I suppose is for about there, then we are okay with that. And it also has the advantage that we can retrieve the value out of the end of that filter and feed it into the start of that filter. So it can be quite an efficient piece of code. So shall we see how that performs? Okay, try not to sort of load you down with looking at bits of code, but worth a quick look. So this is the FIR filter. So all we do each time we call the filter is we have a position in the filter, we grab the last of the existing value out of it, we put the new value out of it, and we have a running total which we subtract the last value from and add the new value from. Simple as that, not huge amounts of summing up of coefficients. Again, if you want to know about that, see the FIR tutorial, link in the description. So we have two of those, and all we get is a pos val and neg val, and then we subtract one from the other and scale it. Very simple. So let's see how it performs. Okay, so let's see how it performs. Don't know what that was. Well, that's certainly a lot better. The nasty grumbling noise has gone. So let's just have a look at the waveforms generated and see how it's performing, I suppose in numbers you'd call it. Okay, so here is the audio which we will play, not recorded, back through the camera's microphone. Okay, certainly sounds a ton better, and if we view the spectral view, yep, I mean you can see there are some faint lines here, so there's some noise on it, but I think for now we're going to move on and just flag up the fact we might need to improve it at some point. And for the record, that is the speed value coming out, and if we play that, yeah, and I turned the level up quite a lot halfway through so you could hear something. There's a bit there, but it's pretty reasonable. Shall we bang that on the spectral view? Yes, there is some noise on there, but again we're just going with it for now. We might revisit it if we have to. So shall we put the string and the rotation together and see if we can make something that'll actually play? Oh, gonna have to do something about that, but here we go. Right, so it's working. So what I propose to do is put a scale along here, calibrate the pitch of this, and then we should have some chance of actually playing some real music. So let's do that. Goodness, first time for a proper piece of music played live. Okay, so before we actually start playing a tune, I've made a couple of changes. We now have a scale along the bottom here which tells us where the notes are, which is very helpful. And instead, if you turn the turntable with with the string not pressed, you used to get a random low note which was equivalent to there, I think. So now I made it so it doesn't. So if you turn it just mutes the note if you take your finger off, because it sounded funny and strange with it just jumping down to this random low note. So we also have a means of calibrating against this scale, which I will show you now. Okay, so if you look on here, I've deleted the calibration file, but it'll save it. So if we look here, that should be 49, and by the default numbers, well, it is, and that should be 83, and it isn't, it's wrong, because that's just some random default numbers. So if we use a pen to get it accurately and put that on there, we can see this number here, and I'm running Camtasia and this at the same time, which is why it keeps stopping. However, we can low, don't know what that is. Oh, yeah, and we put this on here and we hit high. So that's now, you can see, modified the calibration. May I redo that? Okay, and that's this string calibrated. We're not using the other two. So now we should be good to go and play a tune. One last one. Okay, so there you go. We've played a tune on Heresy. Few things to note: that it is just outputting a sine wave, which we instituted just for testing purposes. But still, I mean, you can play quite expressively. It does come up against my inability to play an instrument. I never actually learnt to play an instrument, and sort of really gave up the minute I could use a computer to do the playing. I guess I'll have to practice this one till I can play it reasonably. The player interface, you can hear it warbling where the turntable is speed sensing is still not perfectly smooth, and the occasional drop out from the spring. But I think we're heading in the right direction. More work required, but I think we'll get there. So that's it for this video on the Heresy. Next time we're going to try putting our, I think we call it a bowed bottle model sound generation oscillator we're going to try getting it to drive that. So then the Heresy will actually be playing properly as it's intended, if not well, but at least it's a starting point. I suppose that will, to be right, be the proper start of the project. So that will be for next time, and till then it's goodbye from Triplicate. Goodbye.